talk is different from the point of view that I'm dealing with devices. I will also talk a little bit about how to apply some of the mathematical methods and modeling of these devices for diagnostic processes. But the main topic is going to be gels. And let's see if I can do that. Oh, yes. So I present an overview of modeling and some analysis. I must tell you, if there is an equation, there are very few, it's going to be a tool to explain some mechanism. So I'm going to look at gel swelling with emphasis on mechanical, electrostatic, and chemical issues. First of all, the mechanical behavior of gels results from the interaction of the polymeric network with the fluid solvent. Elasticity, diffusion, and dissipation are the main mechanical features. So right now, for us, a gel is a polymer network that can take a solvent, and it's going to be water in our applications. Now, special kinds of gels, which are the hydrogels, in those ions in the fluid interact with the network, with the polymer network, and changing its elastic properties. So in the case of polyelectrolyte gels, we have bound charges in the network. So then electrostatical and chemical effects highly influence the mechanical behavior. So here I'm going to talk about a system, in this case a physical system, where elastic forces interact with electrostatic and chemical forces, type of reaction binding forces, and how the mechanical behavior changes as a result of this, and what can we do with this. So I come from this problem from the point of view of material sciences, and so when we see a property, we're saying, what can we do with it? Okay, so then how to harness these electrochemical and electromechanical and chemical interactions is relevant to the design of sensor and actuator devices. So here we discuss the modeling of and design of cyclic enzyme-driven sensors actuators for hormone therapies. So first of all, in the outline, so we are going to give a description of what is a gel, and then I am going to talk about governing equations, but mostly for the purposes of describing the mechanisms, the physical and chemical mechanisms that drive all these interactions. Then here we are going to do a little bit stop on the mechanics. In other words, when there is no ions, which happens in some situations and in some applications. And then the next topic is maybe the center of this talk, is the cyclic enzyme-driven drug delivery devices. And so basically what I'm going to talk about is a little engine that is powered by glucose and how it could be used, say, for drug delivery, in this case for the delivery of hormone drugs for therapies that require hormones. And then a little bit about electrochemistry and phase transitions. Then hysteresis and oscillations, and then some conclusions where, where I am going to talk about the follow-up of this. So also there is a good thing about being the last talk, that some things, even if the talk of the subject is very different, some things are already said. And here I just want to point, first of all, to Dr. Regura, who has talked about the first-order phase transition, although in a very different setting, and also to the role of hysteresis. And then here I'm going to talk about oscillations, how this combination of the phase transition and hysteresis can actually give us a dynamical system with oscillations. And well, and then there will be also some parts where Dr. Soler has also talked about that will be coming in. Okay, now here this is a result of teamwork with different people based at the University of Minnesota. Dr. Siegel is a pharmacist, medical doctor at the medical school. Then Jonathan Urban is a scientist at this company, Medtronic, where some of our problems are coming from. This is in Minneapolis. And then Dr. Mori is at the University of Minnesota, also at the School of Mathematics. He is a medical doctor and a mathematician, so I've learned physiology from him and a lot of things. And so we published some articles together. This one is on devices with Dr. Siegel and Dr. Urban, which is to appear now. And And then there is a PhD thesis by Jonathan by John Urban in 2008. And then there's a PhD thesis of my student last summer on volume phase transitions and looking at biomedical applications and the mathematical model of them. And then here we have some of this work is coming up in an article that should appear in the next 4 months, they tell us. Okay, so I will give some other references that have to do more with the mechanical problem, that this has to do really with the electrochemical system. Okay, so finally, gels can be many, many things. Okay? However, for what I mean today, there are cross-linked polymeric networks that hold fluid. So basically, when they absorb fluid, the polymer network stretches, and when the fluid goes, the polymer network contracts. So, and what we want to discuss is what are the different interactions that cause swelling and collapsing, and how we can control them and do things with it. How can we make some devices? Of course, you know more than anybody here that natural gels are found in animal tissue and people, in plants, cell membranes, cartilage. So they are really everywhere. And then synthetic gels are used in manufacturing of these microfluidic devices. Many, many kinds of devices are built with gels, and also body implantable devices. So here I'm talking about 2 problems that have to do with gels. In one, we really produce a gel and we want to get all the facts and all the properties and all the good things about it. And then there is another type of problem where gels just happen. And so then we have to deal with them. And I'll talk about this in a moment. Let's see, there's one other thing. So mechanical effects are associated with the network elasticity, dissipation, solid fluid mixing, fluid diffusion, and transport. So there's here a number of different effects that Dr. Soule has discussed this morning, and I will get back to some of them in this context. And then the electromechanical effects in the polyelectrolyte gels. So polymer network, and here I want to emphasize that in one of the applications, what is really important is that this network has some side groups that are charged, and those may interact with the ions that are present in the fluid. And okay, so here's a little picture of the 2 states of a phase transition. I haven't really shown you how the phase transition happens, but here we have a collapsed gel, which is kind of all crumpled up, and then here we have a solid gel that would, as we see the network, holding water fluid. So in the collapsed or dry state, the volume fraction of the polymer, which you will see this letter is not going to come very often, but is near 1. Okay, so when this phi is near 1, means that we have a large volume fraction of gel. The system is dry. So, and in this case, there is no transport or diffusion across the gel. So for the gel to be able to transport things, we really need to have water. We need to have a swollen state. So the water is the one that does the transport in the gel. And in the swollen gel, well, we have a large volume fraction of fluid, so 1 minus phi is about 1. And then in this case, we have the ability of the gel to transport ions, macromolecules, and whatever we put on it. So now the question is, how can we control swelling, collapsing to make a device? Okay, now, first of all, here I am going to give an example of a situation where a gel happens. So this is one of the technologies of solving a cartilage problem, and of course you know a lot more than, much more than I do around here, but here is just an example of a situation that can happen and that we have computed and worked with a little bit. So this is so somebody has damaged cartilage, at least in part of it, then through this implant, they manage to realign the bone so that the weight of the body falls into the good part of the cartilage. So, however, so when the person gets an implant, and from this point of view, well, it could be any kind of device. So I use this as an example. But here you can think of any kind of device that gets implanted into the body. Usually a device consists of more than one material. There are really no devices that have one single material. So then we have the water in the body is absorbed by this material, and the material becomes gel. Now, every part of the gel, every material component swells, absorbs water at a different ratio. So then what happens is that at interfaces, and in this case you could think of the interface between the implant and the bone itself, there is a high concentration of force. And this high concentration of force may cause what's called a blistering instability at the contact, and eventually make the device fail because it falls apart. So now our question is that how much does it swell and how long it takes to relax? So one issue that Dr. Regura also talked about is the concept of residual stress. So you can imagine that, and in this case was in the bacteriophage, right? So in this case, we put, so the implant is placed between these two supports, between the bone, the two parts of the bone. So then, as it absorbs water, pressure builds inside, so there is a lot of pressure that cannot be relaxed because the bone is confined. And this kind of pressure, so this is called a residual stress, usually gives a lot of mathematical complications, for example, in analysis and in computing, and it's the one that eventually causes the damage. So here is one of the two materials, just to give an example of some realistic situation. These are from Medtronic. So here we have a situation where we have a polymer, an upper polymer, and a silicone base. This is, the top is typical plastic, so this is in a dried environment. So then in part B, this has been submerged into the fluid. So this is what we would like the device, in this case, these two materials to do. In other words, they change shape. We see that the bottom one swells a lot more than the top one. And however, when the stresses at the interface are too big, this is what happens, so they fall apart, and one swells very little and the other one swells a lot. So the problem with this is, or one of the main issues is that this is not a static problem. So if we calculate, say, what would be the stress at equilibrium and then calculate the stress at the interface, this is going to give us only some estimate of the build-up stress. But because this is really a dynamical process and the stress can peak after 10 years. So then the question is how is this behaving in 20 years, which is what the industry computes as the time that we would like the device to last. Okay, here I'm showing this because this is another complication. So these are polyelectrolytes, so here there is ions involved. And so originally we have a nice cylinder, completely straight and fine. And then this is submerged into water. So there are two kinds of solvent, those two kinds of fluid that give rise to two different morphologies. So in this one you see like a bamboo pattern. So it's made of regularly spaced cross-sectional planes consisting of collapsed gels. So we have some narrowings, periodic narrowings along the cylinder that this correspond to the phase. Remember that we talked about the phase transition. So they correspond to the collapse phase of the gel, whereas the white parts are the swollen parts. So here for different compositions, slightly different also nature of the polymer, we see a bubble configuration. So we see constricted regions that are separated by kinds of bubbles or balloons. So again, in here, we have the swollen phase of the gel, and in the constrictions, we have the collapsed phase of the gel. So this is an instability that unfortunately appears in the devices, and one has to live with it and think about what to do, because this really hinders the intent, the purpose that one makes the device with. So here I'm just going to go very quickly through, I have up to 4:15. Okay, so I'm just going to introduce some concepts and to be able to describe the different properties and the different effects that we're trying to measure and use. So we have then the gel, and here the mathematical mixture of polymer and solvent, and we think of it as incompressible. What we mean is that if we take this polymer by itself and we take the fluid by itself, each one of them is incompressible. So in other words, it can only suffer deformations that do not change the volume. So, however, when they are put together, they act as an incompressible system, but each one can have, especially the polymer, can actually have deformations that change the volume a lot. And in polyelectrolytes, as much as 500 times. So now, for example, these kinds of models are used in processes of oil recovery, and then there are phases in it that are not actually incompressible but very compressible. Now, the fluid contains ions that may be diffused and convected, and the polymer network has a bound charge. So it has some units, negative units, side groups that are attached. So now here the one, in the cases where it's going to appear, this subindex 1 means that we're referring to the polymer, and the subindex 2 means we're referring to the solvent. And just for now, I'm going to introduce the volume fraction of the polymer. As I mentioned, 1 minus phi is the volume fraction of the liquid, or phi2, and then everything is basically a function of the point and time. Okay, so in addition to, so then what are the variables? This is the last page of variables. So then we deal with the mechanical deformation. So here we have a domain somewhere in space that is occupied by the polymer before anything happens, and then it gets deformed. For example, when it absorbs water, we pass from something like this to something maybe very big, right? So it's another domain, and here the subindex t means that it could be this at time t at some later time, and so we have some kind of function that brings the undeformed domain, particles in the undeformed domain, to the particles of polymer in the deformed domain. Here we are interested in gradients, the gradient of deformation, and this will come back later in one dimension. The volume fraction that we already introduced, and then we have a balance of mass. So basically what we're saying is that the polymer mass gets conserved, and this is expressed through this equation. So we have a situation where there is no polymer degradation, meaning that if this polymer absorbs water, the whole thing gets a lot bigger, but the mass of polymer there is still the same. So this is expressed by an equation of this form. And now the electrostatic is, we have a family of ions, so n types of ions in fluid concentration. We have the balance, Z, the corresponding balance, and we suppose that, say, one of them is positive, the Z1. I'm not going to worry about the other ones now. Then here, there is one type of ion, say the ion that I label with 1, that can exist as an ion in the fluid, as free ion in the fluid, or can react with the negative groups of the network, and then we call its concentration C0. Okay, so when it has, so we distinguish between that type of ion that can react with the network, we distinguish it between its concentration still as a free ion and its concentration as an ion that has already reacted. So, and then we have the charge of the network, so P is for polymer, and of course we have to take into account the electrostatic potential. All these ions create electric fields and potential, and then the dielectric coefficient of the gel. So that is this epsilon 0. Okay, once we have this, and here I'm just going to talk about the energy to really talk about the interactions that we have among all these different components that we have already seen. So here we see, okay, the following term, P stands for polymer. So this is an elastic term, right? So we have a density of energy that depends on the gradient of deformation, like in a rubber band, the kinds of the harmonic oscillator that we've studied at school, but this is in general in 3 dimensions. F is the gradient of the deformation. And then here we have other types of energy. So this FH of the volume fraction stands for Florey-Huygens, okay? And so this was proposed by Florey in the 50s. He got a Nobel Prize for his work. And basically, this energy explains 2 kinds of interaction, the hydrophilic and the hydrophobic interactions in the gel. In other words, in some situations, the polymer wants to be near the fluid, and in some situations, the polymer wants to have another piece of polymer next to it. So in other words, wants to stay away, wants to keep the water away. So hydrophilic and hydrophobic are here. And of course, these different forces have a very different range. For example, the hydrophobic force, the force that, say, likes, when the polymer likes to be next to itself, this is a very, very short range force. For example, like 2 pieces of Velcro, that you have to put them very, very close so that they get together, that they, in this case, that they stick. However, when they are far away, nothing happens. You have to get them very close, and once they are very close, then they attach very, very strongly. So this is an important force in the building of these devices, and we'll see it again. Then here we have the Coulombic forces, electrostatic, this is the potential, and then this is the ion force. So notice that depends on the family of ion concentrations in the fluid, and this is exactly the type of energy that Dr. Juan Soler was talking about this morning, that from this term comes the diffusion. Okay, so this term is responsible to give us diffusion of ions. And in this case, it's ions that live in the fluid. So, okay, so here we don't need this very much. Sometimes we want to lump it in one energy, but here I want to summarize. So we have elastic energy for the polymer, so we pay energy if this polymer gets very deformed, and also if it gets very compressed. Then hydrophilic, hydrophobic in the gel water, in the polymer water component of the gel, coulombic, and ionic. So the one attached to the movement of the ions. Okay, and here, well, at this point, it's not too important that we know how these forms are. We can talk about it later if you want. So, here you might recognize, for example, the Coulombic force, that's the gradient of the potential. And here you might recognize this ionic force, in other words, the C log C, right? And here we have this factor 1 minus phi because since these ions, with concentration Ca live in the fluid, so we have to have a correction factor, which is the volume fraction of the fluid. Okay, so now, if we talk about, and I pass to this, right, because the first question that we ask is, when we have this energy, right, does this energy have a minimizer? Okay, so again, Dr. Regura talked about that, and yes, under the right conditions, we can minimize that energy. In other words, there is a minimizer, and for example, we need conditions like, for example, the elastic energy gets very, very big if we stretch a lot, and also gets very, very big if we try to compress, say, a finite volume of polymer down to 0. And so that's two basic properties. Now, here, what we did in this work is a numerical simulation. So we wrote those equations that come from that energy. So if you want to find the minimum of an energy, one way is to calculate the critical points and then somehow to convince yourself that that's the minimum, right? So, and here you use the finite element methods, and it's a little bit pale, but this dark part should be the bone, and this light part is the device, the implant that we put in the bone. So now here what we see is a cross section. So basically this is the surface that is at the interface of the bone with the implant. And the red means concentrations of stress. So what the kind of question that we were asking now is how much are these concentrations of stress according to the properties of the polymer, according to the properties of the system. And well, those are measured in pascals. Let's see, and okay, and here I could give a whole talk on the type of finite element method to discretize this. Now, one issue that makes the analysis, and in this case the computations, hard is the fact that this implant has residual stress. Now, here is to give you one of the features that we get out of these computations. For example, here you see a quantity. I haven't made a real big deal about it, but this phi, this would say when the implant is still sitting on the table in the operating room, well, it might have a little bit of water, it might have a little bit of moisture. So then what we see is how much the stress at the interface, the shear stress is the tangential stress, so how much does it depend on the amount of moisture that the polymer may have carried initially. So we see that if we have a polymer that is very dry, because this means phi near 1 means that it will be completely dry. So the drier it is, then the higher are the forces that develop at the interface. So it's the harder it is for the gel to really cope with the fluid that is absorbing. So this and the temperature, for example, are two of the factors that enter in determining what are the right materials, what are the right parameters that that give the right combination of materials. So let's see, for example, how does the industry, how does the company use that? In this case, a device making company. So, for example, so typically to determine two materials that are compatible, in other words, that do not develop an excessive shear stress, so they need about 20 experiments with different materials. Every experiment takes a year, because really this is not, it's not really an equilibrium process. So through the life of the device, those stresses are going to change, so they measure over the year what happens with the stresses. So every experiment has a cost of about $1 million. So it's a lot of money that goes into determining the right kinds of materials for these implants. So what we did with the mathematical model is out of these 20 combinations of materials, we eliminated 15. So from the mathematical model, we predict that 15 are going to have stresses that are actually too big. So then with the 5 that seem reasonable, then the scientists in the company, the polymer scientists, go on and make the experiment. Okay, so here it's a feature about the numerical method, so that since we discretize it, how it converges. Now you see these peaks, so these methods are very well behaved. Okay, what we have here is the residual stress. So if we have negative residual stresses like pressures, then the methods, one has to be very careful because the convergence gets very shaky, and also the stability of the method gets very shaky. So one has to be, and in this case, if the material has to sustain this kind of residual stresses, then a better numerical method has to be in place. So this is just to point out some of the issues that one has to look at when you do mathematics with this. Okay, now here I'm just going to give a page of equations, but to tell you what kinds of forces are acting in these materials. So again, here we have two equations for I1 and I2 for polymer and fluid. And the first equation is the equation of conservation of mass. The rho is the density. It's a product of a constant, which is this proper density times the volume fraction. So now the second we have the balance of linear momentum. So here you can see exactly, let's see if I go, well, the left-hand side, that's the acceleration of the particle. Times the dot means the derivative with respect to time. The divergence of t, this is the force that comes from internal interaction in the system. And then here we have two types of forces. These have psi, we have F1 and F2. So these are the drag forces that the fluid exerts on the polymer and vice versa. And these have to be action-reaction. In other words, they have to add up to 0. And here we put up the forces that are due to the fact that there is ions, or there might be ions, and these ions are interacting, and we have electric forces. So that's basically it. So this, something happened, okay. Yeah, so these three equations basically take care of the mechanics. And so there's one equation for every component. And then here we're saying that, well, there is only fluid or polymer, that there is nothing else, and there is no voids. And now here we have equations which are basically diffusion equations, reaction diffusion equations with transport for the ion components. So the one that is attached to the polymer does not have any diffusion because it stays there. So it's just the conservation of the charge. And these ones for the cis-phase are the diffusion, reaction diffusion equations for the families, for the concentrations of ions in the fluid, the free ions. And, well, here, these forces H, those would be reaction forces. So this system should be the analog to the one that Dr. Soler proposed this morning. I think in your case, you didn't have this term, maybe, but, and then here is the Poisson's equation, right? So here you see the dielectric coefficient of the shell, and so this is basically Laplace's equation, if this was a constant. And in the right-hand side, we have the total electric charge in the system. So charges, the electric charge in the, oops, sorry, I haven't quite handled this well. Yeah, so this is the one, the electric charge due to the ions in the fluid, and the one attached to the polymer. And Q would be basically the charge of the electron. Okay, so Here, notice that these equations are coupled because, for example, before we knew that the elastic forces that come in one of these terms really depend on some type of concentrations, and the velocities are coming here. So it doesn't really quite make sense to see, for a mathematician now, if this is a good system. So what we want to do is to use it as a toolbox to help us design things. And in a moment, I am going to show you that this is the system that we use to design a cyclic delivery device. Here, only one emphasis and one remark, and is that when you have a complicated system like that, the first thing that you want to ask is if it's really, is robust. So again, Dr. Solet talked about this morning of a system that does not satisfy the second law of thermodynamics. In this case, to have the decay of the energy, because you see, we can write the derivative, E is the total energy. The total derivative with respect to time on the energy is equal to a sum of numbers that are positive with a negative sign in front. So it means that this is a system that dissipates energy, so satisfies the second law of thermodynamics. So in a way, now we are confident that we can use it and it's not going to be, physically badly posed. Now, this one, okay, let's see. Here, I'm not going to say this at this point. This is the only thing that I wanted to mention just by passing is that, again, when you have a system that, it's quite big and in a way it's something that you kind of proposed, you want to see if under the right conditions, at the right limits, if it looks like some other things. In other words, what are the cousins and the brothers of this system? And then in this case, in some limit, we get just the fluids, the equation for fluids, or the equation for elasticity, or some other models, or some diffusion models. But, okay, so now this mechanical problem, the system of equations that I showed you, is actually, a lot of it has appeared, except I think this one, and is done in this work. So this paper is the statics, the existence of the minimization of the energy, and the numerical simulations of the static case. And this is a very interesting case. So this is a hyperbolic problem. So incipient dynamics of swelling of gels. And so he did, Heng Zhang, this paper is part of his PhD work in 2007, that's a year later. And this was very interesting because when you have that whole system, right, all that page of equations I gave you before, of course, one thing you want to do immediately is to do a scaling. So you remove the dimensions, and then you get groups of parameters that basically have no dimensions, and then you can say, okay, if this group of parameters is much, much smaller than this other group, I am going to remove this one from the equations, and I get a system that is reasonable. Well, it happens that when you use a gel made of polymers that are, using these devices, in exactly the Medtronic type of devices in bones and also some of the pieces in the pacemaker, it turns out that they are very viscous. And they are so viscous that when you look at the term that has the acceleration, the derivative of the velocity with respect to time, that coefficient is so small that you can actually remove it, can just ignore it. What happens if you use that term? That term influences the solution, influences the process at the 10 to the minus 10 seconds at the beginning. So, and immediately it's forgotten about. So then the company who had given us money to support the student told me, don't even worry about this term. Remove it, because we don't need it. But then, Heng Zhang, he was, he had his own ideas. He said, but I like this term, because then my problem is hyperbolic. So he did this whole thesis on a hyperbolic problem, on a free boundary problem, and so I was a little bit embarrassed with the company, and of course we had to do the work afterwards, but anyhow, we were happy with the work. And so then this is, again, another Brandon Chabaud. He did his PhD on this, and this is one of the articles of his thesis. He defended in 2009. And he's now at Los Alamos. And let's see. And then here we have another PhD thesis that I did in 2010. And this is slightly different of what we're going to do today, but it has some anisotropic versions of those gels. And this is another problem that comes actually related to motion of mycobacteria that is also a model that is based on bacteria gliding bacteria instead of swimming. Okay, so what I mean is that with a set of equations, you can really look at different limits and different parameters and get a whole different set of problems that are very different from each other. Okay, so now here we are going to concentrate in the case that that the gel has ions, so polyelectrolyte gel. So the first thing that we see here is the Pauling phase transition. So in this case, the ions that are relevant are the calcium ions. So, and here we have a picture that tells us that the Pauling fraction of the polymer, right, is going to change with according to this graph. So here we have very small phi, so means very little polymer, so it means that it's very swollen. So here we have up to this concentration of calcium chloride, we have a very swollen polymer. So all of a sudden, this jumps into a high phi. High phi means that there is a lot of polymer, so it's very collapsed. So this first order phase transition is when one type of ion, the relevant type of ion of the system, goes through a critical concentration. So basically what we have is that when there are enough ions, they start neutralizing the negative groups that are attached to the polymer. If there is no ions, if these ions are not neutralized, then the polymer wants to extend very much because those negative groups repel themselves and want to stay away from each other. So, and that's why when, when we have enough of them neutralized, then there is no need for the elastic energy to be so big, for the system to pay so much elasticity, so then it can collapse. And in polyelectrolytes, this happens with a very, very big jump. And this is a relatively new phenomenon, so these kinds of polyelectrolyte gels are probably about 10 years old. They were known before, but really not the type that could give these huge, huge changes. Okay, so now here there is another situation where we have hysteresis. So these are under two different mechanical conditions. So we see that for a while, so here there is a concentration. This goes with the pH of the device. And so, for example, if we follow one of these, we go up to here, and then the system jumps to the top branch. However, when we come down, the system goes up to this end. Okay, and it jumps at a lower pH. Okay, thank you. That's it. Oh, yes, that will help. Thank you. Oh, yes, great. Thank you. Okay, so I'll get back to this in basically at our conclusion. And, okay, so here we have the following situation. So this is the tabletop experiment. Here we have a membrane. This membrane separates a chamber from the external environment, in this case is the body. And what we have is that glucose is coming in from the outside, right? Goes in through the membrane. Of course, it can only go in when the membrane is in the swollen state, right? So then it goes in. And when it's inside, there is an enzymatic reaction, enzyme-driven reaction, that the glucose combined with the oxygen produces hydrogen ions and then a negative ion called gluconate. So when we are in the swollen state, so this is the reaction we're talking about, so this reaction takes place inside the chamber. And so then when the membrane is swollen, the glucose has come in, the reaction can take place, and so then everything can go out because we are in the swollen state. So the drug can go out, in this case the hormone, and hydrogen ions go out, and we're not going to worry about the negative ions for now. Okay, so now we're going to pay attention on what happens to the hydrogen ions as they come out. Well, it turns out that these hydrogen ions, they really quite never make it outside because they react with the negative charges of the network. They neutralize them, and as they neutralize them, they are going to reduce the elastic energy, and that's when the system collapses. So when enough negative charges are concentrated, what we mentioned before, that the system doesn't have to be so expanded, and then it collapses. So when it collapses, then nothing goes through, nothing from the inside, and of course no glucose is coming in. So now let's just take another view to this. So this is again, this is the membrane in the swollen state, and this is the membrane in the collapsed state. Yeah, okay, yeah, I'm almost at the end. So here we see one thing is that really only the collapse, the phase transition, only really happens at the interface between the membrane and the chamber. It does not go through. And at this point, we have that the instabilities, those kind of wave instabilities, are settling in. So this is the reaction that takes place between the negative charges of the network and the hydrogen. So now, we studied the problem. And here I'm not going to, so we have the different hysteresis graphs. So let me just show you one. Let's concentrate in one for a moment. So this is the swelling ratio. So these are equilibrium calculations. So we have the swelling ratio of the membrane versus the external pH. And then you can clearly see here that with critical pHs, the system has a hysteresis pattern. And let me use this because so I can finish here. So now you can see that in this case, on the way up, so on the way increasing the pH, we have the transition right here to this branch, but when we come down, the transition is right here. So Q is the swelling ratio, so Q small is collapsed. So what happens is that it's collapsing at a smaller pH because it really, the chains, the polymer chains, need to get very close to each other so that this long range, the short range force, this Velcro force, can start acting. And that's why it needs to be really, a lot with a small pH in this case. Now, what I want to, and this is the ionization ratio. In other words, what is the ratio of the negative groups attached to the network that are neutralized versus, in other words, the ones that are free versus the ones that are neutralized. So these are is the concentration of the charges in the network that had been already neutralized by a hydrogen. Okay, now this just in passing is the one-dimensional system of the system that I showed you before. So when we've done all that work in general, but in the case of one dimension and for specific family of ions, we get this system. And just want to point out one thing is that we are using, instead of Poisson's equation, we are using a neutrality condition because when the system is smaller than 2 nanometers, then in that case, you have to use Poisson's equation. But if the system is bigger, then there is enough charges around that they kind of compensate each other, and so you can work with the condition that the total charge is 0. This is still a difficult problem mathematically. That's something we looked at before. And in this, I just want to point to this equation. So because here we have to write an equation for all the dynamics in the membrane, and then we have to write an equation for the dynamics in the cell. Okay, so that's what's happening inside the cell, but inside the cell, we have equations for the concentration. So here you see these are the fluxes. So the prime means concentration inside the chamber. And so the concentration increases, the derivative is positive if there is flux of glucose, and also the more flux of hydrogen. Here, you see something that decreases the concentration. So this is a piece of marble that we have to put inside the chamber. It turns out that if you don't put any device that eliminates ions of hydrogen, there is just too many of them and collapse the system. So the marble reacts with hydrogen and takes it away from the system. And this is an issue that I'll discuss in the conclusion. So here we did, under very different kinds of conditions, different concentrations of charges into the network, we finally find that really a cyclic behavior of the whole system. So, for example, here, well, this is time, and now we have one of these graphs is the pH in the chamber, and this graph, in this case, is the swelling ratio measured at the surface. And, well, and here you have for every one of the quantities, for example, for the ratio of ionization, we also have a cyclic structure, and this is for the concentration of negative charges of the net attached to the network. We also have a cyclic process because the charges keep kind of getting attached and detached. One thing that perhaps I didn't mention is that when the hydrogen ions have attached, they don't stay there forever either. They are going to go out, they diffuse out. And then finally here we have the pH at the interface versus the pH at the chamber. So all the quantities give cyclic behavior, and what we did is to adapt the parameters of the system, the material parameters, to fit into the cycle of the different hormones. Now, okay, let me just mention here, so what happens is that this device, it's very nice on a tabletop and it works, but the pH, the working pH is way too low. So the best we can do without the marble is a pH of about 5. So we are now trying to replace the marble, accounting for other types of ions and compounds like the bicarbonates in the body. So far, we haven't had any luck into increasing the operating pH. So in a way, we have to get back to the drawing table and see if with different kind of ions we could get a better operating pH. Let's see. So then we have then a device powered by glucose, and the mechanics is phase transition of first type with hysteresis. Now, let's see, one here. Here to end, right now we are applying this, this model in two kinds of new applications for us, and one is in kidney dialysis, because here we have a membrane that does electrophoresis. So in principle, we have the tools to look at different processes. In the kidney dialysis model, so basically the idea would be to develop a dialysis machine that is much smaller than the present machines. There seem to be many companies that are doing research on that, and we're getting some very interesting problems out of this. For example, how you separate the sodium ions and the potassium ions when your membrane has a filtration size of the order of nanometers. We are trying to use a combination of electric and magnetic fields to be able to tell between sodium and potassium. I don't know if this is ever going to be able to be an application, a real application. And then finally, in the model of edema, basically we looked at the edema as a gel. Of course, here there's a lot of, for example, there's proteins and there is an isotropy. But one of the new issues that we're bringing here is to try to explain why it's so hard to get the water out of the system, of the body of patients that have edema. So our hypothesis is that perhaps the little pools of water that are forming, that are being retained, are going to develop so they show their polar structure. So we argue that since these little pools of water are really, of the size of other parts of the system, they are so small that actually so they are small enough that the dipolar effects can show up. So then we have a ferroelectric system, and this would explain, that's our very simple model so far, of why this water is so strongly attached to the tissue that is so hard to get out. So these are things that we've been playing with, and well, maybe I'll tell you some other time. Thank you very much. I think I'm going too late.
I didn't see clearly in your equations whether, are you taking into account osmotic pressure effects?
Yes.
Probably in these devices?
Yes, in all of them, yes. Let's see, I want to go back, probably this way.
And is there any change in the conditions at which the transition will occur in the presence of osmotic pressure difference between the inside
Yes.
and the
Yes.
outside.
Absolutely, yes. So you see so this is for the one-dimensional model. You can see the elastic, this is the elastic force, the elastic pressure due to the networks being stretched. And this is basically the osmotic pressure. And that's the pressure that we calculate from Van Hoff's law. That is the pressure due to the ions. So basically it says that if you have a concentration of salt outside that is not equal to the sum of the half of the sum of the concentrations of the ions, that is really the origin of the force. And then we work with these reaction diffusion equations with the fluxes and the reaction rates and a neutrality condition. Yeah, but there's basically three contributions to the pressure, at least in these terms. Yeah, definitely it's the phase transition is very much influenced by, basically by all the parameters, especially this one. This one is a number that is being measured, especially in applications to physiology. This is a quantity that determines the relative strength of the hydrophobic to hydrophilic forces in the gel. And it can be changed, say, with the temperature. There's interesting situations where with the temperature you can get very different swelling behaviors. And of course, it changes when you have ion concentrations and charge. Yeah.
And a second question is there any restriction on the electrostatic properties of the drug you want to deliver that will make this oscillatory mechanism feasible? I'm thinking if it's a charge
yes.
a species that you get released out, it may change the internal balance and then
yes.
change the conditions so that it doesn't work?
That's right. Everything is very sensitive to the kinds of ions around. For example, you can change the behavior if you change the concentration of the salt that you add or remove, and you can change the behavior, and this is one of our control parameters of the density of charge, that the negative charge that is attached to the network. So in our computations, we have a range of charges for which this works. Of course, if we get out of these ranges, then you may get a few oscillations, and then the system dies off. So it's and eventually, our graphs maybe they don't show this much, but the system is going to die off. So as you go, say, through quite a few cycles, then these cycles get longer, and eventually you lose the oscillatory behavior.